I'm here with Dr. Romano to do a problem on thermochemistry.
Hi, I'm Dr. Romano, a professor of organic chemistry here at Romano Scientific and the author and creator of the DAT Destroyer books. I want to go over a real nice question with you on thermochemistry. So come around and let's see what we got. In this example, I give you a molecule called phosphine, and we're going to react it with oxygen, and we're going to form two products. We would form a product called tetraphosphorus decaoxide, and we get 6 waters. Now, I give you the delta H of the reaction is minus 4,500 kilojoules. The minute you hear the overall reaction is minus, you know the reaction is exothermic. And if you remembered, an exothermic reaction looks like this, where these are the reactants and these are the products. Notice in an exothermic reaction, the products are at a lower energy level than the reactants. Now, I give you in this example not only the heat of reaction, I give you the heat of formation of water as minus 242 kilojoules per mole, and I give you the heat of formation of the pH3. And I want to find the heat of formation of the P4O10. Now, notice the heat of formation of oxygen is not given, and the heat of formation of the oxygen is 0 because it's a diatomic element in its standard state. What I first do is to recall that the delta H is equal to the sum of the products minus the sum of the delta H of the reactants. So let's plug in. The overall delta H was minus 4,500 equals the products, which is this, we'll call this X. If there was a 2 in front of it, it would have been a 2X, but there's not. So I'll call it X plus 6 times the value of the heat of formation of water, which is negative 242, minus, so these are the products, minus the reactants, which is 4, times the value of the pH3, which is 9.2. You plug the numbers in, so we get minus 4,500 equals X. This comes out to be minus 1452, minus, on the DAT, the numbers will work much nicer, minus 36.8. Then what I would do is bring this and this to the other side and solve for X, and we get minus 3011 kilojoules per mole. All right, let's try one more. Now, in this example, I give you 10 grams of a metal, and the C is 0.13 joules per gram Celsius, and it's initially at 250. So we have a metal that's very hot. We're going to drop it into water, 150 grams. The C is given initially at 20. And I want to find the equilibrium temperature. Common sense tells you that the temperature at the metal must drop, and the amount of water, or the temperature of water, has got to go up because you're putting in a hot metal into cold water. So I can say that the heat lost by the metal is equal to the heat gained by the water. So I'm going to set MC delta T of the metal equal to MC delta T of the water. Now let's plug in. The amount is 10. The C is 0.13. Now if you lose, that means that this must be 250 minus T. It's got to go down. Now, here's where it gets a little tricky. The heat gained by the water. Well, we know the mass of water is 150. The C is 4.18. Now, a nice little trick that I like to do. If you have heat lost, it's got to be the temperature minus T. So if it's heat gained, switch it. Make it T minus 20. Because if you remember, the water is going to be at 20 degrees Celsius, and it's going to be gaining temperature. So that temperature is going to be really high. So you're going to just make sure you're going to switch these. If it's heat lost, it's the number minus T. Where if it was heat gained, it's T minus the number. You remember that trick, you'll never go wrong. Now we just clean it up. We get 1.3. This is 250 minus T. Multiply these together, And when I do the math, we get 20.47. So as you can see, we only had a very small amount of metal. So the temperature only went up a little bit. But the bottom line is that the temperature did go up from the initial 20.47. All right, I hope that gives you a good idea on how to do these problems. All right, good day to you. Bye-bye.